Hey, chemistry. On to the second part of chapter 2 with mixtures. Probably some stuff and some prefixes you've heard about for a long time, probably at least since middle school. So let's get started here. Again, my big giant questions probably should be how can matter be classified, and if there's how can mixtures be, how's matter classified and how can mixtures be separated? I need to have that on this first slide though. Yeah, coffee grounds. If you make a cup of coffee, you shouldn't have any grounds in the coffee, even if you use a coffee maker like mine here. If you use a little Keurig cup, then those grounds stay in the little cup. Coffee's often brewed by mixing hot water with ground coffee beans. So what's to stop the little pieces of coffee grounds from coming into your coffee? Think about that for a minute. Because coffee itself is a mixture. Mixture is a physical blend of two or more components. Notice it's physical. It's not a chemical. It's not a chemical blend. It can be separated. Most samples of matter are mixtures, like chicken noodle soup. Some are easier to recognize than others. As you can see, you got a mixture of chicken, noodles, and broth. It doesn't look all the same. Some mixtures look completely the same through and through, and it's hard to tell that it is a mixture. Recognizing air, you can't see it, but recognizing it as a mixture of gases is tricky. The fact that air can be drier or more humid shows that the amount of water vapor can vary, can change. Based on distribution of their components, mixtures can be classified two ways: heterogeneous or homogeneous. Hetero prefix meaning different, homo prefix meaning same. Chicken noodle soup, you see that the ingredients aren't evenly distributed. We have to put that in a blender and smush it together and make it all look the same. So we would consider this. Let's move over here. Whoops. And that same problem with my little icon here. There we go. There we go. Likely to be different amounts of chicken and noodles in each spoonful, so what you get is a heterogeneous mixture. You can tell that there's a difference. It's obvious by sight. Now, if you did run that through a blender, you'd have a different kind of mixture. That would be homogeneous. Now, olive oil, the substances are evenly distributed. So olive oil doesn't look like a mixture. We've got some lipids. Probably not a lot of water. Why? Because it's an oil. And we know that oil and water don't mix. Vinegar. We know there's a lot of water in that. And what makes vinegar is the presence of acetic acid. It's a weak acid, and we use it in a very weak concentration that dissolves in the water. So we also have a mixture, but you can't tell the difference in the portions. So to kind of think about, what if we mixed the oil and water together? We're going to have a picture of that in a minute. Right now, separately, there are homogeneous mixtures. Homo meaning the same. Mixture in which the composition is uniform or the same throughout. You can't see big glaring differences between portions of it. We can also call it a solution. If you can't see a big difference in the components, we can call that a solution. Many solutions are liquid, but some are gases, like the air around us. Some are solids, like stainless steel. That's a mixture of iron, chromium, and nickel, and we do consider it a mixture. Now we'll talk about phases. Let me pop up here, if I can move my icon up here. My profile picture. There we go. When we talk about phase, we use it to describe any part of a sample with uniform composition and properties. And if you're looking at just a single homogeneous mixture, it consists of one single phase. You can't see the difference in the two or more components. However, let's say, remember I was talking about mixing oil and water together? If you do that, you get a heterogeneous mixture. You can obviously tell, because oil and water won't mix. It won't look all uniform. In fact, the oil will kind of float to the top because it's less dense than water, and the water will stay on the bottom, forming a heterogeneous mixture with two layers, or we could consider this two phases. Oil phase floats on top of the vinegar phase. We could call it the nonpolar, because it doesn't like charged stuff, and the polar phase because that's based on water, and that's okay to have charged stuff there, charged particles. Now, thinking about being at the beach, I know everybody'd like to be there right now. You realize that both ocean water and sand are mixtures. If you wanted to pin it down, which is a homogeneous mixture or solution, and which is the heterogeneous mixture? You can pause just a minute and think about that. I'm going to go on and say salt water. Since you can't see the difference in the two phases, it's homogeneous. But sand, it doesn't look all uniform. You have different pieces. If you put sand under a microscope, you'll probably be very surprised to see what you see. Sand is definitely a heterogeneous mixture. So, our mixture is separated. Like if you have a salad containing an ingredient you don't like, if I see that there's cucumbers on the salad and I'm allergic to cucumbers, I can kind of remove them with a fork, and also I'll probably remove the pieces of lettuce that was touching. And not because I'm picky, just because I'm allergic to it. And if I was really picky, I'd probably say, okay, no red onions either, because I'm allergic to those too. But anything you don't like, you can take off with a fork. If you don't like the tomatoes or the croutons, I don't know who doesn't like croutons, but you can remove those with a fork. Many mixtures are not as easy to separate. To separate olive oil and vinegar, you could pour off the oil layer into another container, or a fancy term for that is decant it. Could also cool the mixture until the oil turns solid and you can kind of scrape it off the top. You might see this during cooking if you're cooking soup or something and you let it cool and you see the kind of a layer of fats and oils kind of stick at the top and you skim that. I see that in a lot of chicken broth too. There's always ways to separate mixtures. Filtration, again, this is how most people get coffee, even in a Keurig cup, because all the coffee and the water, all the action is kind of being kind of held inside that little Keurig cup. That's filtration, process that separates a solid from a liquid in a heterogeneous mixture. Because what happens when you're brewing coffee is you've got hot water going through the unused grounds and then kind of trickling through that filter. The liquid brewed coffee passes that filter, but if you put it in the coffee maker right, filter keeps the coffee grounds from coming through the filter. And you can kind of think about your Keurig cups being the same as a filter. Everything stays in there while the water goes through, and then the liquid brewed coffee goes through into your cup. Again, that's a way to separate mixtures. In a laboratory, it's very similar to using coffee filters. We often place filter paper in a funnel, pour a mixture into a funnel, and then the solids that can't pass through kind of stay in the funnel, and the rest of the particles pass through. Now, distillation is another thing. Distillation, how do we get how do we get clean tap water to drink? And I wouldn't always drink tap water. Some people would rather have the Brita filters. The water I drink, I usually get it out of the Brita filters. Hopefully there's some good filters on our drinking fountains. The tap water is actually a homogeneous mixture of water and the substances dissolved in the water. That's why it tastes the way it does, as opposed to if you ever took a sip of distilled water, it probably wouldn't taste very good. One way to separate water from other components is through distillation. Let's say you had a whole bunch of gunk and stuff that you didn't want people drinking. So you might go through a really high-scale distillation. In that case, a liquid is boiled to produce a vapor that is then condensed down to be a liquid. Now let's kind of walk through these steps. Here's an apparatus for a small-scale distillation. Now, if we needed to do this for like city drinking water, we'd probably have a really big apparatus, huge. But you probably hear about this kind of distillation or desalination plants like in cities close to oceans, because there's a whole bunch of water available. It's just not drinkable. In this case, you've got a mix. You got your tap water, considered a mixture. Let's say you want to make sure you get the lead and all the heavy stuff out of there. So what you do is you put a heat source under the tap water, and you heat it to where you turn it into vapor. Remember, not a gas. We would consider it's in the gas phase, but we consider steam as water vapor. Heat that to 100 Celsius to try to keep it there. Because then what we've got here is water. water getting boiled away, essentially boiled away from the bad stuff or the heavy gunk. And how do we get the water back? Here we've got this thing called a cold water condenser. This is like a tube in a tube where the steam is going. We're kind of surrounded by another jacket of water. You've got cold water getting pumped in and cold water getting pumped out. That's a condenser. That is going to cool down the steam back to liquid, and then it goes back to the receiver flask. And it's collected there. There you have nice, clean distilled water. You're like, well, what about the gunk? Why does it stay behind? It stays behind in the distillation flask because you've actually got to get it hotter than 100 Celsius to get it to vaporize. And what you may wind up with is maybe some solids back there, which you really need to heat it up a lot. When we talk about those solid substances, their boiling points are much higher than the boiling point of water. So they stay behind, and that's why we keep the temperature at 100 Celsius. And we turn water into steam and then cool it back down to get it separated. That's another method of separation. Now I'm looking through the reading section. I'm looking for chromatography. Sadly but truly, I don't see chromatography in your book itself. So we're going to talk about that. We're going to kind of hit that, and I'll probably do a chromatography demo during our next class period. Again, if you have any questions, just send me an email. Bye.